Good afternoon, class. Today is November the 4th, and so this is the video for November the 5th. And we'll first go over quiz 2. And problem 1 was just a qualitative problem that I expected you from the review and everything else to know the answer of. For patterned etching of silicon nitride, you would want to use a plasma B because you get much less undercut and much more control over the etch. And number 2, you should know by now that KOA etching stops on the A111 plane. Number 3, I taught you that for patterned plasma etching, this is related to, this is determining etch masks, and what I taught you was that for 3,5 semiconductor, plasma etching usually involves chlorine, and so you want to use silicon nitride as an etch mask. And number 4, when stripping photoresist, acetone, methanol, isopropyl. So those 4 questions were just sort of knowledge-based questions to make sure that you have remembered all the qualitative things that we've learned. Now, number 5, you were presented with 2 oxidation patterns. One looked like this, and one looked like this. And you were supposed to tell me which one was the correct one. This is C versus Z. And you were told that the plots stop at the oxidation depth. And of course the answer is this one, because you learned that R is K times C sub Z, and it also is equal to the flux, negative D dC dZ. And so since this one has a lower slope, it has to have a lower value at the oxidation depth. And so this one is wrong because it has a lower slope, and so a lower R, which is inconsistent with having a higher C sub Z. So that was the answer to number 5. Number 6, you had to do a little bit of derivation. The question was, does the rate of oxidation at time equals 0 depend on the diffusion coefficient? And so if you use your formula for Z, Z is equal to negative Z naught plus Z naught times the square root of 1 plus T over T. Okay, and for small t, T is much less than T. Okay, this is equal to, or approximately equal to, negative Z naught plus Z naught, and then you use that binomial approximation. So Z is approximately equal to, the Z naughts cancel, Z naught over 2 capital T. Like we went over in the homework, it's linear with time. And Z naught is D over K, and T is D over 2, this funny molar volume, K squared CS. And so if you plug those in, for small time, it's Z is approximately equal to D over K over 2, well, the 2's cancel, D over K squared mu CS, and the D's cancel. So Z is proportional to, or is goes as time as k squared mu cs over k, or k mu, funny mu, cs. And so the answer was false, B. False. D of t does not depend upon d for small t. And you could have reasoned that out because, you know, at time equals 0, you were at the surface, right? At time equals 0, you're at the surface, and so how can it depend on the diffusion coefficient? I mean, diffusion coefficient means it's having to diffuse through the silicon, and at t equals 0, you're right at the surface, so it only depends upon the concentration at the surface and the reaction rate. All right, and number 7, you were supposed to determine the Q. Does it depend on temperature, or how it depends on temperature? And we went through that the Q is proportional to L, which is 2 square root of dt, and the D goes as d naught e to the negative ea over kt. So Q then is proportional to the square root of d, or e to negative ea over 2 kt. Well, I'll write it out. Ea over kt to the 1/2, or e to the minus ea over 2 kt, and the answer was B. All right, and then finally 8. Okay, you have no gas diffusion. And I mean, I don't want to use the word trick question with Q. Okay, I don't want to use the word trick. I hope this wasn't a trick question for people, because I mean, the whole point is that you're performing. You did a gas diffusion resulting in Q, and then a gas off diffusion, and I said, I mean, kind of, I don't know, not to trick you, but I mean, at time t1, Q is, the integral is Q, and then at this next time, is it, what is it? And of course the answer is Q. I mean, it doesn't change. Once you turn the gas off, Q is the same. It's independent of time, and so the answer was C. So we can maybe discuss the quiz more tomorrow if you want to, during the chat session. But I thought it was a set of good questions to make sure you understood everything. All right, now, new material. So, as I discussed in the announcement over the weekend, Quiz 2 marked sort of a natural breakpoint in the semester or in the course, because you know, we've covered a set of things so far that you know, like lithography and etching and things like that, which occur both in the research lab as well as in at an Intel foundry, for example. And now kind of marks kind of the subjects we're going to go through next, including ion implantation today, are things that you typically don't see in your research lab, but are very much part of a foundry's operation, like Intel. And so, well, let's just walk through it. Ion implantation is just what it sounds like. Okay, you know, I'll draw a picture over here. I looked up on the web. Basically, an ion implanter. Well, it is kind of shaped like a curve like this. So basically, your wafer is over here, and over here you have a gas inlet. You have an ionizing chamber So that basically ionizes your input gas. And then basically, well, roughly, you have an accelerator, which is basically a series of plates of like V1, V2, V3, V4, with kind of a hole in the middle, so that those ions are accelerated and form an ion beam. And what you do is, just in case there's any neutrals, you have like a little magnet somewhere here, magnet. And that magnet causes the, put the wafer over here. So this is the wafer. And that magnet causes the ions to bend and hit the substrate, and any neutrals that is any unionized gas that somehow got accelerated that misses the wafer. And so you have basically ions hitting the wafer. And inside the wafer, okay, if we look at the let's look at silicon. So silicon, so we have a lattice. And you have, like, say, an ion beam of boron hitting the substrate. And the wafer is grounded, so it acts to bring in electrons and neutralize, neutralize the boron. But what happens is that the boron kind of drives into, and usually it goes interstitial like this. So you might have a bunch of boron atoms. Now what happens is that, so this is before annealing. And then after annealing, what happens is that if you do the annealing properly, you may have damaged the wafer with the implantation, and what happens is that you get silicon. So after annealing, you get boron. So here they would be interstitial, meaning not on the lattice side. And then when you do the annealing at a high temperature, it rearranges the atoms, and so the boron atoms wind up on crystal sites. Which is what you want, of course, because you learned that that's how doping works. Doping works because you put like a boron atom, and so this becomes p-type then. Meaning if these boron atoms are like interstitial in the crystal, they can't really dope the crystal so much, or they can, but it's not controlled. You want to perform an annealing so that first of all you repair any damage caused by the ion beam to the crystal, and second of all you put those boron atoms on lattice sites so that they act like dopant atoms then. And so it's a method of doping. Okay. And it has completely replaced diffusion. Diffuse for example, for CMOS, for integrated circuits. And the reason why is primarily the control and I mean, let me just draw it. The main reason is, okay, when you, first of all, the reason is you can use photoresist as a mask. And this is in the notes, so I'm just telling you what's already, it's basically on the first page in ion implantation. For diffusion requires an oxide mask. Whereas for ion implantation, you can use a photoresist mask. And so the idea is that here are your ions, and so they're stopped in the photoresist, and they're allowed to come in here. And the main reason you use ion implantation is because, okay, let me put over here oxide, dopant gas. So in diffusion, for example, if this was an N wafer and you were putting in P, all right, you would get a profile like this, where the lateral movement of the dopant ions, or the dopant atoms, equals the depth. And so, I mean, which kind of makes sense, right? I mean, you're diffusing it. Diffusion, you can't have diffusion that is anisotropic, but most of the time diffusion is isotropic, meaning it goes in both directions equally. Whereas for ion implantation, just sort of naturally you can kind of see, even after the annealing step, the rule of thumb, they had it here, is 1/3. Meaning if it goes down this far, okay, so about 1/3, so this is much less, well, it's 1/3 compared to 1. 1/3 is less than 1. So you get much more control over the lateral position of your dopant atoms, which means if you're fabricating a device, you can have that much more precision, of course. And that's basically, they have some equations in the notes here, and they're worthwhile to a certain extent understanding. But the main thing is that it's completely replaced. Now, there is still, besides in the laboratory, commercial use of diffusion. Solar cells. I actually sent Dr. Hagedis, who's our resident expert on solar cells, still use diffusion. And he said that the reason why is because they tried ion implantation for doping of solar cells. Now, if you think about it, for a solar cell, you don't care about this lateral movement so much because you're really just blanket coating the whole wafer. But basically, the reason is that you have fewer defects with ion implantation, even after the annealing, and so you get better solar cells with diffusion. But otherwise, commercially, ion implantation has completely replaced doping. Now, we don't have one on the university that I'm aware of, and so if you ever have ion implantation done, as I have done in my career, not for doping, for other reasons, this is, like I said in my my announcement, the first step I've never actually done myself. I've never operated an ion implanter. And so, my knowledge of it is the same as what you have now, sort of more theoretical, in terms of how it works. And the one time I had it done at Bell Laboratories, we sent it out to an ion implantation commercial service, and that's probably what you would do if you had it done in your research. But if you go to work for example, for Intel or other foundries, what you would find is that all the doping that they do is with ion implantation. And I thought that, so the lecture's kind of short because, that's all really I want to go through on ion implantation. But I thought it was a nice point, or a nice time to talk about real foundries. In the sense of, okay, now we're starting to talk about things that happen in real semiconductor fabrication foundries, meaning like, where the chips in your phone or your computer are made. And so I thought it would be kind of fun. Boy. Let me see if I can show this. Unfortunately, my living room is a little bit sunny. Let me see if I can get the focus going here. So let's start over. Okay, so I got my focus back. So what I'm going to do is I'm going to avoid going in front of the camera so that we don't lose focus. And hopefully we'll be able to see what's on the screen. Okay, so I'm just going to sit here and maybe kind of point to this things a little bit and go through it. Okay, so what I wanted to do is in today's lecture, besides talking about ion implantation, is talk about where the state of the art is with regard to integrated circuit fabrication, which of course should be part of this course. I mean, you should understand what's going on in the real world. Also because, I mean, you use these chips in your daily life, in your cell phone, and your computer. You can't read this here. You can read the file if you want. But for example, here's the Pentium D. And the Pentium D came out in 2006. And it had approximately 1 billion transistors on it. So this chart is called Moore's Law. And basically, it's a plot. I just took this right off the web, out of the Wikipedia article, and it's a plot of since 1970, when integrated circuits sort of started, to today. Well, not quite today. This goes up to 2018. The progression of the number of transistors, the transistor count, versus year. And as you can see, in agreement with Moore's prediction back in actually the 60s, it has been doubling every 2 years. And if you know a little bit about exponentials, so that's this exponential function here. Whoops. That's this exponential function up here, if you can see my cursor. Which is basically 10 to the 9, t minus 2009, roughly. So this is saying 1 billion transistors at the year 2009, with a time constant here of 2.9 years, which would result in a doubling every 2 years. And you can relate this to the what's called the line width, or the feature size, which is on this chart. This chart is showing the nominal feature size, and when foundries are discussed, they're discussed in terms of what's called sometimes a line rule or a feature size, And for example, this article here talks about Intel's 10 nanometer process. So remember, a nanometer is, 100 angstroms, and so it's somewhere on the order of, 200 atoms wide. And so this is showing that back in 1970, they could make features as small as 10 microns. And then sometime around 2005, 2 or so, they reached, 0.1 micron or 100 nanometers. And then around 2017, reached 10 nanometers. And this little article I took off the web is projecting that TSMC, now TSMC is actually, if you're interested in the status of the chip fabrication industry, to a certain extent, what appears to be happening this year is that Intel is considering abandoning fabrication and becoming only a design house. And so they would send their designs to TSMC, Taiwan, I forget what that stands for, Taiwan chip maker, to have their chips fabricated. So that would be pretty interesting. And the investors in Intel are not happy about that because, the whole point of having your own chip fabrication is that, you are in control of the future of the technology, and so, you can make the best chips because you continue to develop the technology. Whereas if you basically contract your chip making off to another company, well, then this company is making chips for everyone, and so they may not give you the best process. But anyway, TSMC, Intel does not appear to have a firm plan going below 10 nanometers, whereas TSMC is projecting 3 nanometers at 2022. Now, remember, the lattice constant, you've learned this, of silicon is somewhere around 5 angstroms or 0.5 nanometers. So 3 nanometers is 6 atoms wide. Now, this feature size does not translate into the minimum area per transistor. If you go through this plot, basically you take this, divide this by the die area, which we'll talk about that in a minute. That's how big the chip is. That has been going up roughly, doubling every say 7 years. The area per transistor is this, and so basically if you divide that by the line width squared, around 2009, it took 1600 square line width squares, and so that's basically a transistor would fit into 40 line widths on a side. And that has been going down itself, but getting back to this number here, this whole plot, there are basically 2 things that govern it. One is the line width, which has been going down, as you've seen here, allowing smaller transistors to be made. Well, there's actually 3 things. The other thing is that the area in terms of L squared required per transistor has been going down, okay, with a time constant of around 7. All right. But the other thing is the die area has been going up. And so if you take, now the die area is currently, apparently, I didn't know this because I haven't really been keeping track of this. We're currently up at a die size of, getting close to 900 square millimeters. I mean, this is supposed to be millimeter squared here, which basically means 30. And let me see if I can bring it up here. All right. So basically, a chip size of 3 centimeters on a side. that's apparently where we are right now, which is, if you know how big a centimeter is, I mean, basically, that's a pretty big chip. And so for a lot of applications, not for cell phones, of course. I mean, three centimeters on a side would would fill half the cell phone practically. But in terms of very high-end ICs, we are at what is called the reticle limit. The reticle limit is basically, going back to our discussion of projection lithography, how big an area can be that a projection lithographic machine can produce a good pattern on. Meaning, and I asked a few of my colleagues over the weekend what results in the reticle limit, and it's basically optics. It is the optics of the projection lithographic machine is limited to 3 centimeters on a side. And so we are at an interesting point in time, and I drew this curve here, kind of roughly between these points. We are in 2020, right now, we are apparently right now this year at the reticle limit. Now, what that means is that this curve right now at 2020 has to bend over, because you see the increase here has been due to the decrease of the line width, which is continuing to go on at least till 2022, and we'll talk about that in a second. But also because the chip has gotten bigger, allowing more transistors at a given size. So this calculation here is basically showing that if we are limited to 900 square millimeters, all right, the number of transistors on a chip in the year 2020 is 44 billion. Okay, and that's, there's 50 billion here. And now it can only double every 2.8 years because we can't make the chips any bigger. So that's kind of interesting. This phenomenon is called the end of Moore's law, and basically it's been talked about for the last 20 years, maybe longer, 25 years, where back here, I remember in the 90s in Bell Laboratories, we of course knew about this curve, and we kept saying, well, projecting it going forward, there has to be some limit, and we are apparently right now reaching one of the limits, which is that we can't make the chips any bigger, and that itself is limited apparently by the optics and basically optical physics is limiting the size of the chip in the projection lithographic machine. Now, so basically, we're going from a doubling every 2 years now to every 2.8 years. But okay, we only got that till 2022, because at 2022 we're at 3 nanometers. It's becoming very difficult to understand how we can make features smaller than that. Now, I did want to say, just digress a little bit here. You can see this thing called the planar MOSFET limit. Now, those of you that have taken some transistor courses know about MOSFETs, and know that MOSFETs are generally look like this. You have source, drain, you have gate, and basically the gate allows this channel to flow, and that's your voltage controlled current device or transistor. And apparently, and also I was unaware of this, we reached the limit, the planar MOSFET limit, meaning using devices where the channel was in the plane of the chip back in 2010 or so, and I wasn't actually perfectly clear on that. The 10 nanometer process is using what's called FinFETs, which are these devices here. Those devices are where you fabricate a a semiconductor ridge. The gray area here is semiconductor, so you've etched it to form a ridge, and now this is your channel, not planar anymore, but vertical above the surface of the chip, and the gate is wrapped around it so that you have you can make basically the gate smaller. So we've changed our technology from planar FETs to FinFETs, and this is projecting even further variations going forward. And so, you know, the question is, all right, 3 nanometers, and you know we've hit the reticle limit. So this curve is going to bend over, and now, because we're reaching the reticle limit, and in a few years, I guess, I mean, we'll reach the line width limit, how small a feature we can make. And so this thing is going to, in the next few years, start bending over probably and reach a physical limit. Now, if you think about it, our entire technological industry, to a certain extent, I mean, cell phones, computers, everything has been based upon Moore's law. Think about your phone, right? I mean, you know, there's a new iPhone every year or something like that. Okay, I mean, a large part of what enables that is the fact that they can make chips with more transistors on them, and so have more capabilities and things like that. There are other technological improvements that take place each year, but I mean, since 1970, you can see here, I mean, for the last, you know, basically 40 years or 50 years, this curve has been behind much of our technological improvements commercially as well, and because of that, I mean, you can extend it forward. Much of our economic progress that has been done over the last 50 years is this curve, and this curve is stopping. So what I wanted to discuss, and we'll discuss it in the chat session tomorrow, is, and I'll go ahead and stand up now, because I won't worry about losing my focus too much. I discussed over the weekend the grading, and the grading will be the homework 36%, each quiz, and there'll be a third quiz, and I'll be announcing the date of that soon. Each quiz is 13%, and so that brings you 36 plus 39 up to I can't do 30 75, right? Sorry, and so that leaves 25%. And that 25% can be some type of final exam, but I'm considering, and I thought it might be more instructive to have a final project instead of a final exam. And the final project, I think, I'm leaning toward is related to this curve here. That as a project, what I would like you to do is to turn in like a 2-page paper on the expectation in the next, say, 5 years, you know, 2025, of this curve. And now that sounds like kind of an open-ended kind of thing. As I said, I wouldn't want more than 2 pages. And I was thinking of even making it the kind of thing where you would seek out some expert, which could be a professor at a different university that's more tuned into you know, where this is going right now. We don't have very much IC research going on here, so a place like Berkeley, for example, or Stanford, or you know, if you're from China, back in China, but basically it would be kind of a library project, and discussing what is limiting, what is going to limit. Now, we already know one limitation that's happening today, which is that we can't make the chips any bigger. You could write a project on that. You could discuss, you know, what is behind that. Is it the optics and the projection lithography? But basically, some sort of discussion of why this curve is slowing down its upward growth would be the project. And part of the point of a final project like that is that you can't cheat because cheating is encouraged. I mean, the whole idea is that you are to, I mean, if you can find, if you know of someone working at Intel and you can talk to them, anyone you can find, anything you can find that provides, intelligent discourse on this question, that's what you would be writing up. All right, so we'll discuss this more in the chat class tomorrow, and that's it for today.